Everyone, and welcome to this module on continuum mechanics. In this module, we're going to discuss the Eulerian strain tensor. So, we are in the current or deformed configuration, and we're going to derive a stress tensor. And here, as the next topic, we have the change of area and volume due to deformation. So, we're going to establish a connection between the deformed and undeformed or the current and reference configuration, the area and volume in the reference and current configuration. So basically, we're going to say how we can derive the area or the volume in the reference configuration if we have, for example, the area or the volume in the current configuration and vice versa. All right, with this in mind, let's get started with the Eulerian strain tensor. We basically show this by small e star in here. We also had its counterpart as capital E star. It was the Lagrangian or the large deformation strain tensor. All right. You already know that we have our small dx in the current configuration is equal to f, the deformation gradient, d capital X. So if we had an element in the reference configuration, we had this tensor here that transforms this element, d capital X, in the reference configuration, and it take it to the to the current configuration. But we also can write this as, so if I put this, let's say f inverse here, dx is equal to f inverse dx in here, sorry, f dx. So this became I, and then finally I had dx in here. So I can write this as f inverse d small x is equal to d capital X in here. And if I write this in initial notation, I'm gonna have f inverse ij dxj is equal to dxi, because this is a vector, this is also a vector. Here we have a second order tensor. And from here, you can get that f inverse ij is basically the partial derivative of xi, capital Xi, with respect to small xj. And I put a partial derivative because here we have different components. So if I write this, if I expand this f inverse ij in here, so I have something like x capital X1 with respect to small x1. Then I have, capital X1 with respect to x2, capital X1 with respect to small x3. You have capital X2 with respect to x1, x2 with respect to small x2, x2 with respect to small x3, then capital X3 with respect to x1, capital X3 with respect to x2, capital X3 with respect to small x3. So now let us consider, so we already established this connection here. Let me just put rectangular around it. So here we have dx is equal to f inverse d small x. So if I have two elements, let's say dx1, d capital X1, and d capital X2, so here I have these two, the dot product of these two elements is equal to, let me just bring this bit down because I'm going to write some assumptions here. So here we have assumptions. And remember here that in Eulerian strain tensor, we are going to establish a strain tensor in the spatial coordinate system or in the deformed configuration. So I will write this here later. So I have dx1 dot dx2, where you know that dx1 is ds1 n dx1 dot dx2, and dx2 is ds2 m, for example. So here, you see that these n and m, these dx1 and dx2 are not perpendicular to each other as we had in previous tensors. For example, we assumed in B, C, and E tensor were, for example, ds1, e1, and ds2, e2, and these were orthogonal to each other. But here we assume that dx1, d small x1, and d small x2 in the current configuration or in the deformed configuration, they are perpendicular to each other. So here you see that the elements in the current configuration are orthogonal to each other. So elements in deformed or in current configuration are orthogonal. And we're going to establish a connection between these elements. All right, so we have dx1 dot dx2 is equal to f inverse d small x2, sorry, x1 dot f inverse dx2. I can write this as dx1 f inverse transpose dot f, sorry, dot, this is f inverse dx2, and remember these are the number of elements, these are not exponents. dx1 dot f inverse transpose, so I can write this f inverse transpose as f transpose inverse f inverse dx2 is equal to dx1 dot, so here I can write this as f inverse f, sorry, f, f transpose inverse. So if I expand this become f transpose inverse f inverse, which is this one. So this is dx1 dot f, f transpose inverse dx2. So I remove these in here. And this is nothing but b, the left Cauchy-Green strain tensor. So we have dx1 dot b inverse dx2. So now I'm going to multiply both sides of the equation with a minus sign, and also I'm going to add dx1 dot, sorry, dx1 dot dx2, and also multiply both sides by a minus sign. So I'm going to get dx1 dot dx2 minus, here I have d capital X1 dot d capital X2 is equal to, here I have dx1 dot dx2 minus dx1 dot b inverse dx2. All right, So here I get dx1 dot dx2 minus dx1 dot d capital X2 is equal to, I can write this as I can put an I in here. So dx1 dot I minus b inverse dx2. So if I call this as 2e star, where e star is the Eulerian. So we call I minus b inverse equal to 2e star, where e star is Eulerian strain tensor. All right, so if I do this, then finally get dx1 dot dx2 minus d capital X1 dot dx2 is equal to dx1, 2 goes in here, dot e star dx2. So now let's get to the diagonals and off diagonals interpretation of this E star in here. So let's go for the diagonals. All right. So if I assume that dx1 is equal to ds1 e1, as we already assumed in here, and dx2 is equal to dx1, and we also have d capital X1 is equal to ds1 n. So we don't know whether these these elements, which are now parallel to each other in the current configuration, we have no idea how they were in the reference configuration. But here dx2 is equal to dx1, and this becomes more prominent in the off-diagonal elements. So here we have, if I write in here, so we have ds1 squared. I'm just writing from here, so let me call this a star. So from star minus ds1 capital S1 squared is equal to 2. Then I have ds1 small s1 squared e1 dot e star e1. Therefore, we have e star 1 equal to ds1 squared minus d capital S1 squared divided by 2d small s1 squared in here. And the same equation can be established for e star 2 and e star 3. So let's go for the off diagonals of diagonals. So again here we have dx1, maybe I write it here, is equal to d small x s1 e1, dx2 is equal to ds2 e2. So you see that they are orthogonal to each other in the current configuration, but we have no idea about them. Sorry, we have to write them in stone. Let me just check in here, correct. So, but in reference configuration, we have no idea about them. ds1n, and this is dx2 is equal to ds2m. So we have, so again from star, I have ds1. So here you see that e1 and e2 are orthogonal, so this term will be removed. So minus ds1 d capital S2 n dot m, where it is equal to n m their cosine beta. So it is the cosine beta where n and m, these are the magnitudes, so they are 1, and we have the cosine beta, which is the angle between n and m, is equal to 2 ds1, ds2, e star 1, 2. Therefore, e star 1, 2 is equal to minus d capital S1, d capital S2 divided by 2 ds1, ds2 cosine beta, where cosine beta is the angle between n and m in the reference configuration. So basically, here in the deformed configuration, you have E1 and E2. This is the deformed configuration. And in the initial configuration, we have something like this. This is, for example, N, and this is M. And this is beta. This is undeformed or reference configuration. All right. Now let's find ESR in the form of tensorial as well as initial notation. So we already mentioned that if we have this reference configuration, and here we have the current configuration, and this is our, x1 and x2, our, you know, uh, origin, then we have this element here, capital X, where this element in the reference configuration, in the current configuration is X, and this is basically, this is basically U. So basically x plus u was equal to a small x. And from here, we know that x is equal to small x minus u. And remember here that this u is now characterized by the spatial coordinate x1, x2, x3. These are all small, and then t. So we are in a spatial coordinate. So if I take the derivative of this, if we take the derivative of this with respect to, j, small x j, so we have xi, because we know that these are all I, right? These are all vectors. So partial derivative of xi with respect to small xj is equal to partial derivative of xi with respect to xj minus partial derivative of ui with respect to xj. And here, you know that this becomes delta ij. So if I write this in initial notation, this is partial derivative of xi with respect to small xj, which is here f inverse. So this is f inverse equal to, this is delta ij, the identity tensor, and then we have this is the gradient, this is del u, and since here we have small x, so I put in small x in here. All right, so now we know that we have b inverse in here, which is basically f transpose inverse. So we have b inverse, which is f transpose inverse. Let me check. F transpose inverse. So this becomes f transpose inverse. Then we have f inverse, which is equal to f inverse transpose f inverse. So we have f inverse in here, which is I minus del u in spatial coordinate transpose times I minus del u in spatial coordinate. So this is equal to I minus, so del u in reference configuration minus del u in reference configuration transpose plus del u reference configuration transpose times del u in reference configuration. Perfect. And we know that 2e star is equal to I minus b inverse is equal to, so if I write I, this I goes, it cancels out with this I, then all this becomes positive and this becomes minus. So we have del u in reference in spatial coordinate minus del u in reference and spatial coordinate transpose minus this plus del u spatial transpose del u spatial. Perfect. So now I can write this as so E star is half of del u in spatial plus del u in spatial transpose minus half of del u in spatial transpose del u in spatial. Perfect. And in shell notation, we have, let me just write it here. E star ij is equal to half of, so we have ui, then xj plus, we have uj with respect to xi, because this is transpose, minus half of, so we're going to get something like, I don't know if I have another color, maybe this one. All right, so we have T J. So this T I J should equal to del U spatial transpose IM del U X. This is MJ. This is transpose. So this becomes del U spatial MI del U spatial mj, which is equal to partial derivative of um with respect to xi. Then we have partial derivative of m with respect to xj. So here I can write this as m with respect to xi. Then I have partial derivative of with respect to mj. So these are also two important equations here. All right. There is something that I would like to mention here. Maybe this color is better. All right. So if you see here for infinitesimal deformation, we can say that the partial derivative of ui with respect to xj is somehow equal to partial derivative of ui with respect to xj. This is the capital Xj. And partial derivative of uj with respect to xi is equal to, is somehow equal to, is approximately equal to partial derivative of uj with respect to capital Xi. Therefore, we can write that for infinitesimal deformation, we can say that E star is approximately equal to E, not E star, because that was the Lagrangian one. All right, so E star is equal to E. So the Eulerian string tensor is approximately equal to the uh, infinitesimal strain tensor. All right, so next we have the change of area due to deformation. So as I already mentioned, we're going to establish a connection between two areas in the deform and reference in the deform and undeformed, or reference and current configuration. So if you remember, if we have two vectors here, this is, for example, A and this is B, we have two vectors. So the cross product A cross B, it created a parallelogram here where we could say that the area, it was equal to the area of gram, it was equal to the area of this parallelogram here. And we had basically C, which was basically orthogonal to these A and B. And you know this from your high school or your undergraduate course, and I guess that this one was all right. So with this on mind, we're going to utilize the same strategy to find the area in the deform as well as in the current configuration. So, sorry, the deform and undeformed configuration. So, in the reference configuration, so in the reference configuration, we have dx1 cross dx2, and this is cross, remember. So this will give us the area under the curve, the area which is created by these two elements, dx1 and dx2, the area of the parallelogram here. So we call this d. Let me just shift this a bit to the right. So this is dA0. If we assume that dx1 is basically ds1 e1 cross ds2 e2, for example, then we're going to have ds1 ds2 and e1 cross e2 is e3. So it becomes something like this is e1, this is e2, and this is e3, the right hand basis that we already dealt with so far. So we get something like this. So if we call this dA0, here we have a vector, and this is the magnitude. So finally, dA0 is equal to the magnitude of dA0 E3. In the current configuration, we're going to have dA, which is equal to basically dx1 cross dx2. So we use the transformation matrix f dx1 cross f dx2. Remember, this is cross. So I can write this as ds1 f e1 cross ds. Maybe I can write this down. So this is ds1. So this is the magnitude, ds1 f e1 cross ds2 cross ds2 f e2. So I can write this as ds1 ds2 f e1 cross fe2. And here, this is dA0, remember. So this is dA0 fe1 cross fe2. All right. This is also another equation. So if I can find this fe1 cross fe2, then I can say that I already established a connection between these, the area in the deformed configuration and the area in the reference configuration. So we already know that dA is equal to, this is the vector, so it can be characterized by its magnitude and the vector normal, because we don't know whether this E1 and E2, what happens to them in the reference configuration. So that's why I chose this n as an arbitrary kind of tensor, as an arbitrary kind of direction. So, all right. So I have 1 and 2. So if I put 2 in 1, so instead of dA, this vector in here, so I have dAn is equal to dA0 fe1 cross fe2. So here, this one is magnitude and this one is magnitude. So I can write this as n is equal to dA0 divided by dA fe1 cross fe2. And we also know that fe1 dot fe1 cross fe2 is equal to 0, because here we have a kind of vector which is orthogonal to e1 and e2, like the ones we had in here. And we know that since e1 is basically orthogonal to this arbitrary kind of let's say vector in here, so the dot product is 0. They are orthogonal, so fe1 is orthogonal to fe1 cross fe2, so it is equal to 0. So this is equal to fe2 dot fe1 cross fe2. Remember this, and yeah, this is equal to 0. So we can say here that fe1 dot n is equal, therefore, according to this, maybe I should change its color to something else. So fe1 dot n is equal to fe2 dot n is equal to 0. This is something like this. So you have fe1 and you have fe2, and this is n. We don't know it yet, but we know that they're orthogonal to each, that fe1 and fe2, they are orthogonal to n. So from here, I can write e1 dot f transpose n. I can write this as, e1 f transpose n is equal to e2 dot f transpose n is equal to 0. Also from here, I know that e1, therefore e1 is orthogonal to f transpose n, and e2 is orthogonal to f transpose n, because the dot product is equal to 0. So with this in mind, if if we get back to equation here to 3, so from 3, I have n equal to dA0 divided by dA fe1 cross fe2. So if I add fe3 dot here, so this is magnitude. I can take this a bit to the right. So I have fe3 dot. Yes. So I can write this. So f3 dot n is equal to this equation here. So here I have an expression where I can show that this is the determinant of f. This is the determinant of f. How? So if I choose another color, so suppose that you have f, let's say f, or let's write it with an arbitrary kind of tensor like ta. So if you have ta dot tb cross tc, so this is equal to the determinant of t. We're going to find this out. All right. So I have ta dot tb cross tc, where t is a second order tensor and a is a first order tensor. So I can write this as tai e I dot tbj ej cross tck ek. All right, so these are magnitude. I can take this out, ai bj ck, and I have then, sorry, t ei dot tej cross tek. So if you remember, we had this t ei, it was equal to tj I e j. And here, since we have j, I'm going to write this with r, for example. So here we have this TEI is equal to TRIEI. So I have, so with this in mind, so if I put it on an arrow and I shift, no, I don't need to shift this. So I'm going to have AI, BJ, CK. So TEI is equal to TRIER dot. I have TEJ, so I can write this, for example, with M, MJEM, cross, I can write this with N, TNKEN. Then I'm going to have AIBJCK, TRITMJTNK. This is ER dot EM cross EN. So this is EM cross EN. So this can be written as epsilon MNZ, for example, EZ. And I can write this as AIBJCKTRITJTNK epsilon MNZ ER dot EZ. So this becomes delta RZ. So R is equal to Z. So this is equal to AIBJCKTRITMJTNK. This is epsilon MNR. And since here we have, you know, RMN, and this is a right-hand side basis R, then I have M, and then I have, oh, sorry, then I have N. So here epsilon M and R Mn is equal to epsilon M and R is equal to epsilon NRM. This is epsilon M and R is equal to RMN. So I have here AI, BJ, CK, TRI, TNJ, TNK, epsilon RMN. All right. So since epsilon RMN is equal to epsilon, M and R is equal to epsilon NRM. Make this a bit neater. All right. And this is equal to since here we have, E, E1, E2, and E3. So this is equal to the determinant of F. Here we have the determinant of F, or the determinant of T in here. All right. So if we get back in here, so we have 3 is equal, sorry, from 3, we have FE3 dot N is equal to dA0 divided by dA. This is FE3, which is the determinant of F. So here I can write this as, maybe I can write it here. So E3 dot F transpose N is equal to dA0 divided by dA, the determinant of F. And I can write this as F transpose N dot E3 dot E3 is equal to dA, dA determinant of F E3. So this become 1. So I can also shift this to the left. Then I finally get this equation here. So I can write that, maybe this is not the final one. So because I would like to further simplify this. So we have dA0 divided by dA. So I have F transpose N is equal to this. So if I get rid of this F transpose in here, so I get F, so let me put an F transpose inverse in here. So then I have to put an F transpose inverse in here. So this becomes IN is equal to N is equal to dA0 divided by dA, the determinant of F, F transpose inverse, which is the same as F inverse transpose E3. So then I have N dA or DAN, it's better. So I have dA0, the determinant of F inverse transpose E3. And finally, I get dA is equal to dA0, the determinant of F inverse transpose E3. This is since we have the magnitude, so the magnitude goes in here. This is the final equation, with the assumption that here we had E3, so we had E1 and E2, and this was E3. So here you see that N was totally arbitrary. But suppose that the undeformed here, sorry, the undeformed or the reference configuration, it is E3 here. So it was in the direction of E3. But in general, suppose that instead of E3, you have, for example, N0. So you have N0 in here. And we have N in the reference configuration, in the current configuration. So dAn is equal to dA0, the determinant of F inverse transpose N. And this can be written as dA is equal to dA0, the determinant of F, the magnitude of F inverse transpose N0. So initially, we established this connection for for a vector for two vectors E1 and E2, where their cross product was E3. But now here we say that for any arbitrary kind of vectors, whatever you have, where their normal is N0, so we establish a connection or a relation between the deformed and undeformed area. All right. We can also write this equation in the form of, we know that the determinant of f is the Jacobian. We already showed this in the previous modules. So you can simply substitute this with the Jacobian. All right. So now let's get to the change of volume. The change of volume due to deformation. So again, from your undergraduate or high school, you remember that if you have a parallel pipe like this is so A dot B cross C is the volume of parallel pipe. So if this is B and this is C and this is A, so you get the volume of this parallel pipe. We use the same strategy here. So in reference configuration, we basically have dv0 is equal to dx1, for example, dot dx2 cross dx3, where we have ds1e1 dot ds2e2 cross ds3e3, sorry, e3, where we can write this as ds1, ds2, ds3, e1 dot e2 cross e3 is the determinant, which is equal to 1. So this is equal to ds1, ds2, and ds3. In current configuration, we have dv is equal to, so we have df dx1, so maybe it's better to write it, since this is volume, so it is magnitude. We put it into these brackets, straight brackets. So we have dx dx1 cross dx, sorry, dot dx2 cross dx3. So I can write this as f dx1 pipe dx1 dot add f dx2 cross f dx3. Perfect. And then I can write this as ds1, ds2, and ds3. Then I have f e1 dot f e2 cross f e3. Similar to what we did in here. So we have dsfe1 and then ds2fe2 and then ds3fe3. And then we get to here where this is the determinant of f. This is the determinant of f. Sorry. And this is nothing but dv0. Therefore, dv is equal to dv0, the determinant of f. Or we can write this as the Jacobian dv0, because we know that the Jacobian is the determinant of f, right? We also have, we can also use the left and right Cauchy-Green deformation tensors, because we know that C is equal to F transpose F and B is equal to F transpose. And the determinant of C is basically the determinant of F and F transpose. So since this is F and F transpose, we can say that the determinant of C is equal to the determinant of B is equal to the determinant of F squared. Therefore, we can write this dV is equal to the square root of the determinant of C. dV0 is equal to the square root of determinant of B dV0. For an incompressible material, we know that the Jacobian is equal to 0. So dV is equal to dV0. And due to the conservation of mass, so from conservation of mass, we know that m is equal to m0, right? So rho dV is equal to rho dV0, rho 0 dV0, because density might change. So here, instead of dV, we write the Jacobian dV0 is equal to rho 0 dV0. We get rid of these, since we know that they are not equal to 0. So rho is equal to rho 0 divided by the Jacobian. And this Jacobian is basically the determinant of f is equal to the square root of the determinant of C, or the square root of the determinant of B. All right. There's one more thing that I would like to mention, and it's related to this determinant of f, or the determinant of the deformation gradient. So if the determinant of f is equal to 0, so it means that dv is equal to 0. So this is in paradox with the conservation of mass principle, because we see that there was some material in the reference configuration, and now it is just gone. So this is impossible. Uh, Also, this is impossible. So if the determinant is 0, then dv is equal to 0, which is, or that is, in contrast with the principle of conservation of mass. Uh, Therefore, the determinant of f couldn't be 0. So if the determinant of f is less than 0, so it is negative, or the determinant of f, is positive in the reference configuration, it should also be the same in current configuration. So if we are in the reference configuration, and here we have the current configuration. So if the determinant of f is positive, here we have the determinant to be also positive. So if the determinant is negative, here it should also be negative. So otherwise, it should also be the same in the current configuration, because if the determinant of f changes sign, so if in the reference configuration it is positive, and then it becomes negative in the current configuration of it, or it is negative in the reference configuration and it becomes positive in the current configuration, it shows that f, the determinant of f, becomes negative somewhere, which is in contrast to the principle of conservation of mass, or the above, see above statement. So remember that the determinant can't be equal to 0. The determinant of f can be equal to 0, because then the volume is equal to 0, and then it shows the material is gone, which is in contrast to the principle of the conservation of mass. And remember, if it is the determinant of f, if its sign is positive, it should remain the same in the current configuration. If in the reference configuration the determinant of f is negative, then it should also be negative in the current configuration. There's one more thing here. If you recall, the dilatation for infinitesimal deformation. If you remember, it was E, and it was equal to the trace of E, or it was equal to the divergence of U. Here, the dilatation for large deformation is basically equal to, so if we show it with dv divided by dv0 is equal to the uh, determinant of f is equal to the Jacobian. And the Jacobian is basically exact for large deformation.